So I've talked about angular speed and tangential speed, or tangential velocity, in uniform circular motion, but I haven't yet actually talked about acceleration in detail. So we're going to start with that, and that's going to lead us into a discussion of centripetal acceleration. So there's two ways to think about this. First, let's just think about what's happening in terms of angle. So our angular speed, which was this lowercase omega, is constant. We can define an angular acceleration of alpha, which is literally just the change in omega with time. Well, that's going to be 0 because our angular velocity is constant. So if we wanted to ask in uniform circular motion what's happening with our angular acceleration, well, it's 0. But what if we think in terms of x, y? If I come over here and look at 3 points, at this first point, I see that my velocity is pointing kind of in the positive x-hat direction and also in the positive y-hat direction. But then at this later moment, I see that my velocity is pointed in the negative x-hat direction. At this third moment, it's pointed in the positive x-hat direction, negative y-hat direction. So clearly, my velocity vector is changing. So even though for uniform circular motion, we would say that our angular acceleration is equal to 0, our velocity vector itself is changing, so we need to define an acceleration. And just to remind you, velocity is the speed, the magnitude, and the direction. So even though in all of these cases we would say that these green vectors, which are our tangential velocities, have the same magnitude, i.e. the same speed, the direction is different. So the velocity vector is changing because the direction is changing. This brings us to centripetal acceleration. Centripetal acceleration represents the change in my velocity vector as an object moves through a circle, even in uniform circular motion, due to the change of direction of just the velocity vectors. So for instance, if I imagine taking one point here at the very top and doing my velocity vector subtraction such that my change in velocity is equal to my final minus my initial, I then see that I need to take my initial vector and flip it, and that our sum of these brings us straight down. So at this top point, we have a change in velocity that is straight down. If you repeat this process for every single point, it always points towards the center of the circle. So the direction is towards the center of the circle. The magnitude is given by either velocity squared r, where this is effectively the tangential, and in this case speed, since we don't have the vector symbol, just the speed. And the radius here is the radius, the r is radius of whatever circle it's moving in. And again, right now we're thinking about uniform circular motion, though this does extend to other types of circular motion. And just based on the definition of this tangential v and how it relates to angular speed, we can re-express this in terms of angular speed and the radius. Now, I'm actually going to go through the derivation of this in a separate video because it will take a little bit of time. But first I want to just highlight the most important things to know about this, even if you don't know exactly where it comes from. So again, the first thing to know is that this centripetal acceleration points towards the center of the circle. This velocity vector subtraction shows us that. The second thing is that if we're in uniform circular motion, the magnitude is constant. Why? Well, our tangential speed would be constant, or our angular speed, and our radius needs to be constant. So if what it depends on is constant, it itself is constant. Finally, centrifugal acceleration is not a thing. And I understand that sometimes you might misspeak. Perhaps in your previous physics class you learned about centrifugal acceleration, but that's not a thing. Later when we talk about forces, the book has a little aside about what's called fictitious forces, and I almost just want none of you to even read that section because I find that it just causes very much confusion. So we're talking about centripetal acceleration, which is different than centrifugal acceleration, because this is just not a thing. I will be very happy if you never say it or write it. I understand that sometimes you'll make a mistake in terminology, but the scary thing is that if you start saying acceleration is pointing away from the center of the circle, well, that is just wrong. So now that we've defined centripetal acceleration, there's one really important point that I want to make before I do the derivation of where it comes from, and that is that this is not a constant acceleration. So in particular, note that the direction of it is constantly changing. So even though the magnitude is constant, right, we can say that the magnitude is constant, nice, but the direction is not constant. And that's really important. We have established some equations that we can use in the two-dimensional kinematic situation of, say, xy coordinates in the case of constant acceleration. And here we don't have constant acceleration. So we can't actually make any really nice simplifications in xy space. Doing any type of circular motion problem in terms of x and y components is a nightmare. Please, please, please don't do it. Not at this level of physics. You shouldn't ever need to. So the second thing is that because we can't really use xy components, we want to be working with these circular motion variables and equations, some of which I've already shown you and some of which will be developed in future videos. So this is why we need to think about angular position and angular speed and angular acceleration, because if you try to talk about x and y acceleration, it's going to look really, really ugly, since those will depend on time. So please be careful about this and don't oversimplify by trying to use x and y.